In 1960, two men sank nearly 7 miles into the Pacific Ocean. Jacques Piccard and Don Walsh crammed themselves into a steel sphere the size of a refrigerator, dropped into the Mariana Trench, and touched the deepest point on the planet. When they got back to the surface, the world celebrated, magazines ran the photos, governments shook their hands, and then, basically nobody went back for 50 years. We put 12 people on the moon between 1969 and 1972. We've sent robots to Mars, parked telescopes at the edge of observable space, mapped the surface of Pluto down to its frozen nitrogen plains. But the ocean, the thing literally beneath us, covering 71% of the planet we actually live on, remains roughly 80% unmapped, unobserved, and unexplored. That's not a guess. That's NOAA's own number. So what happened? NASA's annual budget hovers somewhere around $25 billion. NOAA, the agency responsible for understanding the entire ocean, the entire atmosphere, and every coastline in America, gets roughly $7 billion. And ocean exploration specifically, that's a fraction of a fraction. We're talking hundreds of millions, not billions. In government spending terms, that's a rounding error. And here's the thing, nobody in Congress wants to say out loud, space sells. Space has always sold. Kennedy didn't stand in front of a crowd and say, "We choose to map the mid-Atlantic ridge." He said the moon, because the moon is up there, visible, romantic. You can point at it. A kid can point at it. The abyssal plain 4,000 meters below the North Atlantic doesn't have that. You can't see it. You can't point at it. And the photographs, when they exist at all, look like muddy parking lots sprinkled with the occasional translucent worm. That's a marketing problem, and marketing problems kill funding. Dr. Robert Ballard, the guy who found the Titanic, has talked about this for decades. He's pointed out repeatedly that the United States has invested more money in a single Mars rover than it has in the entire history of crewed deep ocean science. Not annually. Total. The budgets tell the story plainly. After the Cold War enthusiasm for sonar mapping and submarine warfare died down, deep ocean research became what policymakers call a discretionary luxury. Translation. First thing cut when someone needs to fund a fighter jet. Alright, let's say Congress wakes up tomorrow and writes a blank check. Let's say ocean science suddenly has unlimited funding. Are we exploring the deep ocean by next Tuesday? No, not even close. Because the engineering is frankly nightmarish. At sea level, the atmosphere pushes down on your body at about 14.7 pounds per square inch. You don't notice it because you grew up in it. Your body equalized before you could talk. At the bottom of the Mariana Trench, 36,000 feet down, the pressure reaches roughly 15,750 pounds per square inch. For every single square inch of whatever vehicle you send down there, that's the equivalent of stacking about 50 jumbo jets on top of a person. Materials behave differently under that kind of force. Metal warps, seals fail, glass, even thick, industrial purpose-built glass, develops microfractures that propagate in ways engineers can't always predict. Electronics short out because pressure forces moisture through seals that would be perfectly fine at 300 meters, and the temperature swings are vicious. Surface water near the equator might be 85 degrees Fahrenheit. The abyssal zone sits just above freezing. Hydrothermal vents on the ocean floor blast superheated water at 700 degrees directly adjacent to near freezing ambient water. That thermal shock alone destroys equipment that costs millions. Building a vehicle that survives all of this, carries instruments, carries humans, maintains life support, provides light in total darkness, and can actually move with any precision, that's not an engineering problem. That's 100 engineering problems stacked on top of each other, each one requiring its own team of specialists. Compare that to space. Space is a vacuum. A vacuum is, in engineering terms, relatively predictable. You're fighting one major enemy, the absence of everything. In deep ocean work, you're fighting the overwhelming presence of everything. Water is heavy. Water is corrosive. Water gets in everywhere. James Cameron, yes, the director, spent 7 years and roughly $10 million of his own money building a submersible to revisit the Mariana Trench in 2012. 7 years, 10 million, for a single dive that lasted a few hours, and portions of the vehicle were damaged on descent. That's not a scalable model, that's a billionaire's passion project. Here's something that genuinely surprises people when they hear it for the first time. We have higher resolution maps of Mars than we do of our own ocean floor. That sounds like an exaggeration design. To get clicks. It isn't. The surface of Mars has been mapped to approximately 5 meters per pixel resolution by orbiting spacecraft. The global ocean floor, most of it is mapped at a resolution of roughly 5 kilometers per pixel. That's a 1,000-fold difference. The reason is deceptively simple. Electromagnetic radiation, light, radar, the stuff satellites use to map everything else, Doesn't penetrate seawater well. Visible light gives out within a couple hundred meters at best. Radar bounces off the surface. The only tool that works at depth is sound, sonar. And sonar is slow. A satellite can map millions of square kilometers in a single orbital pass. A sonar-equipped research vessel maps a narrow strip of ocean floor directly beneath it, traveling at maybe 10 knots. To map the entire ocean floor at reasonable resolution using ship-based sonar would take, and this is not a joke, an estimated 100 to 200 ship years of continuous survey work. The Schmidt Ocean Institute, the Nippon Foundation, GEPCO. These organizations have been running a collaborative project called Seabed 2030, trying to map the entire ocean floor by the year 2030. When the project launched in 2017, roughly 6% of the ocean floor was mapped to modern standards. By 2024, they'd push that number to about 26%. Progress? Absolutely. But that still leaves an area larger than the surface of Mars completely unknown, not poorly understood. Unknown. Blank. And mapping is just step one. Mapping tells you the shape of the floor. It doesn't tell you what's living there, what the chemistry looks like, what geological processes are active. For that, you need to physically go there, or at least send a robot. And the robots are slow, expensive, and fragile. A huge amount of what we do know about the deep ocean exists because the US Navy wanted to find Soviet submarines. During the Cold War, underwater acoustics became a matter of national survival. The Navy funded massive research programs. SOSUS, the sound surveillance system, was a network of hydrophone arrays planted across the Atlantic and Pacific, specifically to track Soviet ballistic missile submarines. Understanding how sound moved through deep water required understanding deep water itself. Thermoclines, salinity layers, bottom topography, all of it suddenly mattered because a missed submarine could mean a missed nuclear launch. That era produced an enormous amount of oceanographic data, bathymetric surveys, current mapping, geological sampling of the ocean floor. Researchers at Woods Hole, Scripps, Lamont Doherty, they benefited directly because their work overlapped with military priorities. When the Soviet Union collapsed, so did the urgency. Submarine tracking didn't stop, obviously, but the frantic pace of Cold War oceanography cooled down significantly. Budgets shrank. Research vessels were decommissioned or reassigned. The pipeline of military-funded ocean data slowed to a trickle. And civilian science never fully replaced that pipeline, because civilian science has to justify every dollar to a committee, and committees want deliverables, timelines, and broader impact statements, none of which are easy to produce when your research area is a pitch-black abyss 6,000 meters underwater where your instruments might get crushed. This one doesn't get discussed enough. The deep ocean is actively, physically hostile to human presence in ways that go beyond pressure and temperature. At certain depths, the water itself becomes corrosive to specific alloys. Sulfide-rich environments near hydrothermal vents eat through coatings and housings. Biological fouling, organisms colonizing the exterior of equipment, begins within hours of deployment in some regions. Tube worms, bacterial mats, crustaceans, they don't care that your sensor package costs $400,000. They see a hard surface and they move in. Long-duration monitoring equipment left on the ocean floor has come back encrusted, corroded, and sometimes physically displaced by biological and geological activity. One research group deploying sensors in the Pacific described recovering a monitoring station that had been completely buried by a sediment flow within 14 months. The environment doesn't just make exploration difficult, it actively undoes your work while you're not looking. Space exploration has a glamour pipeline. Astronauts train for years in public view. They have public relations teams. Children dress as astronauts for Halloween. There are astronaut movies, astronaut memoirs, astronaut Instagram accounts. Deep-sea pilots? Most people can't name one. The talent pipeline for crewed ocean exploration is razor thin. The number of humans who have been below 6,000 meters, the abyssal zone, is smaller than the number who have been to space, significantly smaller. As of 2025, roughly 700 people have been to space. Fewer than 30 have been below 6,000 meters. The working conditions are genuinely miserable. Submersible interiors are cramped, cold, and dark, except for instrument lighting. Dives can last 8 to 12 hours. Communication with the surface is limited and delayed. If something goes wrong at depth, rescue is functionally impossible within any useful time frame. Recruitment into deep ocean piloting and research isn't competitive with aerospace, tech, or even conventional marine biology. The pay is worse. The recognition is worse. The career trajectory is uncertain. And the physical risks, while statistically rare, are categorically unsurvivable when they occur. Nobody ejects from a submersible at 10,000 meters. Every time someone actually goes down there and looks, they find something extraordinary. In 2023, a Schmidt Ocean Institute expedition in the Pacific discovered over 100 previously unknown species in a single dive series. Not over the course of a multi-year program, a single expedition. Gelatinous creatures with no common names. Worms that metabolize chemicals that would kill most surface organisms. Fish adapted to pressures that would flatten a car. The pharmaceutical implications alone are staggering. Compounds derived from deep-sea organisms have shown efficacy in early-stage research against cancers, antibiotic-resistant bacteria, and inflammatory diseases. A compound from a deep-sea sponge became the basis for Halavin, an FDA-approved breast cancer drug. That came from one organism, collected from one site, on one dive. The mineral wealth is almost obscene. Polymetallic nodules scattered across abyssal plains contain manganese, nickel, cobalt, and rare earth elements, the exact materials needed for batteries, electronics, and renewable energy infrastructure. Conservative estimates put the value of Pacific Ocean floor mineral deposits in the trillions, and the climate science potential is enormous. The deep ocean absorbs roughly 90% of excess heat from global warming and about 30% of atmospheric carbon dioxide. Understanding how deep ocean circulation, chemistry, and biology process that heat and carbon is fundamental to predicting what happens to global climate over the next century. We're trying to model the future of Earth's climate while ignoring the single largest component of the system. It's like trying to forecast weather while refusing to look at the sky. The honest answer is, yes, some people are. But it's patchy and underfunded, and driven mostly by private money and a handful of stubborn institutions. Victor Vescovo, a private equity investor and explorer, funded and completed the Five Deeps expedition in 2019, reaching the deepest point in every ocean aboard his submersible limiting factor. That vehicle has since completed more dives to full ocean depth than all other vehicles in history combined. Private money, personal obsession. The Schmidt Ocean Institute, funded by Eric and Wendy Schmidt, operates the research vessel Falkor and makes its data publicly available. They've produced some of the most significant deep ocean discoveries of the past decade. Private money, philanthropic mission, ocean exploration. Trust, founded by Ballard, runs the Nautilus exploration vessel and streams its dives live. They've engaged millions of viewers. Private money, stubborn idealism, Rev Ocean, a Norwegian initiative, built one of the largest research vessels ever constructed, and has faced repeated delays and funding complications. The pattern is consistent. Private individuals with personal passion and disposable wealth drive disproportionate amounts of deep ocean progress. Governments contribute incrementally. International cooperation exists on paper and struggles in practice. NOAA's ocean exploration program does critical work with a budget that wouldn't cover the catering on a mid-budget action film.